Welcome to this explainer. Have you ever stopped to think about the invisible, utterly fascinating physics behind something you probably see every single day? Today, we're diving into the life of a truly remarkable guy who brought all those hidden physics into the light. We are talking about Dr. Stan David and his absolutely transformative legacy in the world of material science.
Think about it for a second. When you picture welding, what actually comes to mind? Is it just a practical engineering task? Sparks flying, a guy in a heavy mask, intense heat, just fusing two pieces of metal together so a bridge doesn't collapse? Or is it something deeper? Is it actually this highly complex, rigorous symphony of physical metallurgy, fluid dynamics, and fundamental science? Well, for a long time, the whole world kind of thought it was just the first one. But our entire perspective shifted, and that is entirely thanks to the work of one visionary researcher.
And that researcher was Dr. Stan David. Over an incredible multi-decade career, most of it based right at the prestigious Oak Ridge National Laboratory, Dr. David completely rewrote the rulebook. He didn't just study welding, he literally proved that it is a profound and elegant science. He took this incredibly practical blue-collar activity and elevated it into a rigorous scientific discipline, totally grounded in solidification science and physical metallurgy.
Section 1. Elevating Welding to Science. Okay, so to really grasp his impact, we've got to look at his absolute passion for solidification science, which is basically asking, how does liquid metal actually become solid? The problem is, welding involves blinding light and extreme intense heat. You can't exactly just peer inside a pool of liquid steel with a microscope to see what's going on. So Dr. David and Professor Rohit Trivedi came up with this brilliant workaround. They used a transparent model system. By mixing a chemical called succinylenale with 1.2 weight % acetone, they created this low-temperature analog. Basically, it was a completely transparent material that simulated the exact solidification behavior of metallic alloys, but it did it at a low enough temperature that they could actually study it safely.
And I'm telling you, this transparent analog was a massive game changer. By running linear laser welds right through this clear material, researchers could literally sit there and watch the solid-liquid interface behave exactly like freezing metal alloys. It's like having X-ray vision. Through these experimental observations, they locked down the fundamental relationships between thermal gradients, solidification rates, and crystallographic orientation. They literally made the invisible visible.
Section 2. Fluid Dynamics, Shaping Welds.
If we take a look even deeper into the weld itself, we find these incredible internal fluid dynamics that are literally carving out the final shape of the metal. Transport phenomena research shows us that these crazy internal flows aren't random at all. They're dictated by mathematical concepts called the Marangoni and Prandtl numbers. Depending on the exact values of these numbers, the fluid flow inside that molten pool drastically changes. It completely dictates whether the weld's fusion zone cools into a simple hemispherical shape, a bracket shape, or even this highly complex W-shaped morphology. It is pure, highly predictable fluid dynamics at work.
And all those fluid dynamics and thermal gradients, they leave behind a permanent physical record. If you look at the microstructure of a single crystal weld in, say, a nickel-based superalloy, the level of detail is just stunning. You get these primary, secondary, and tertiary dendritic arms that look almost like microscopic frost, and they grow exactly according to the fundamental laws Dr. David helped establish. This work was absolutely crucial because it finally explained why materials segregate, why they form these specific microstructures, and, most importantly for engineers, why welds sometimes crack. To capture all these deep insights, he was constantly pushing the boundaries of what technology could do. For instance, using time-resolved 3D diffraction data collected on a DP880 steel sample, Dr. David, along with Professor Wei Zhang, pioneered advanced techniques like neutron-based stress measurement. This let them study phase transformations in real time right as the welding was happening. He was always on the hunt for the next tool that would help uncover those deeper scientific truths.
Section 3. Earning Unprecedented Scientific Respect.
Now, if we pivot from the lab bench out into the broader global scientific community, Dr. David's work laid the foundation for some incredibly influential publications. Getting applied engineering topics published in top-tier, super-demanding journals like Science and Reviews of Modern Physics, that is an incredibly rare feat. It really proves just how much he had single-handedly elevated the science of welding.
In fact, the crucial point here is captured perfectly by this quote. In that one highly memorable issue of Reviews of Modern Physics, Stan's review article stood entirely alone in one very specific, very impressive way. It was the only contribution authored without a Nobel laureate co-author. Seriously, let that sink in for a second. His scientific rigor was so undeniable, so foundational, that it sat there comfortably alongside the work of literal Nobel Prize winners, completely on its own merit. That right there is a reflection of just extraordinary respect.
And that immense respect translated into a massive global reach. As the founding editor-in-chief of the journal Science and Technology of Welding and Joining, he built a dedicated, peer-reviewed international forum that is still a leading journal today. And his global recognition was everywhere, from the Joining and Welding Science Award out of Osaka University to the William Irgong Memorial Award from the American Welding Society to fellowships in multiple scientific societies. The impact of his scientific rigor literally crossed the globe.
Section 4. The true measure of legacy.
So we've seen the science, right? We've seen the publications and the literal wall full of awards. But is that what actually defines a lifetime of work? Well, shortly after Dr. David retired, he made a phone call to a colleague, and he asked, "Guess what I did with all those award plaques that used to hang on my office walls?" He had packed them all into boxes. And the realization there is actually really powerful. A wall full of plaques, while, incredibly well-deserved, doesn't define a career. When the office is all packed up, the metal and the wood just stay in those boxes. Awards alone aren't the true measure of a legacy.
Instead, true legacy is found in the communities you build. Dr. David founded the Trends in Welding Research Conferences. And this wasn't just some dry technical meeting, it was a vibrant community. It was this amazing space where ideas crossed borders, bridged totally different scientific disciplines, and connected different generations of scientists. On top of that, for about 25 years, he served as a task leader for the Department of Energy's Basic Energy Sciences Welding Science program. He was literally shaping national research priorities and funding cutting-edge work at places like MIT, Penn State, Ohio State, you name it. He built the infrastructure so that other people could succeed.
So ultimately, his lasting impact is visible not just in rigorous laboratories or on the pages of prestigious journals, but in the people he surrounded himself with. He educated, he mentored, and he inspired entire generations of researchers. The absolute greatest measure of his scientific leadership is the sheer number of people he influenced to push the boundaries of curiosity even further.
Dr. Stan David transformed welding from an everyday engineering task into a profound, elegant science. But more importantly, he empowered others to keep asking the hard questions. So as we wrap up this explainer, I really want to leave you with this provocative thought. Whether you are in science, business, or the arts, what will be the true measure of your own life's work? Will it be the plaque sitting in a box, or will it be the people you inspire along the way? Think about it. Thanks for joining me on this explainer, and definitely keep exploring the science all around you.